Hi, this is Erik Peterson, and I'm going to talk about filtering spam SMS or text messages. This is interesting for a couple reasons. The first is that there are just so many of them, and especially when you consider newer apps like WhatsApp, um, there are tons of these short messages floating around now. The second reason this is interesting is because these messages are short, and so potentially, at least, there's not a lot of data available in order to determine if a message is legitimate or not. For this project, I've identified three goals. The first, most obviously, is we want to filter out spam messages. The second, and one that the paper doesn't really go into, is that we really need to take care not to block many and ideally no valid text messages. As you can imagine, if you block even 1% of a customer's text messages, they're going to get upset when they find out that they haven't reached their receiver and they have no idea why. And the third goal is the algorithm needs to run very quickly. So whether it's on a server or on a mobile device, this filtering can't take long because this is text messaging and it's expected to be near instant. And anything that slows that down or potentially um, uses up battery power in trying to apply a model is a no-go here. Now a little bit about the test data I used. This was a corpus of 5,574 messages brought together by two authors in particular, and a corpus they wrote a paper about in 2011. Again, it's 5,574 messages. 747 of those are marked as spam. In fact, all the messages are marked as either spam or a ham, which is their term for a legitimate message. And like the authors, when I ran my tests, I split the data into 30% training data and 70% test data. Let me tell you a little bit about my testing setup. I'm running all these tests on my laptop. It's a pretty recent Core i5 laptop. The real limiting factor, though, was the 8 gigabytes of RAM, which seemed to be pushing it for some of the algorithms. Also has an SSD, which I'm sure helped. It was interesting that even though I have a 4-core machine, only one or maybe two cores tended to be hit at a time. And also to do some text preprocessing, I wrote a small Java program to clean up the text file some. And then the further text preprocessing and the algorithms were all run in RapidMiner Studio, the free edition. Now let me talk a little bit about the text preprocessing that I did in code. First one was that the beginning of the line, and maybe in the first line in the file, had some junk characters that the program took out. Characters that weren't printable, so weren't obvious until you started looking at the data. Um, there are also several lines that use a space in between the label, spam or ham, and then the actual message. Took those out and replaced them with tabs. There were some HTML codes floating around in there for the less than sign, greater than sign, and ampersand. And so I went ahead and removed those. May or may not, probably didn't make a difference, but it makes them more true to life. There were quite a few unprintable characters or very strange characters or character combinations. I'm guessing this is the result of file encoding problem, either on their end when they created the corpus or when I downloaded it to my Windows machine. Um, and so I did my best to replace those with characters that made sense. And if I couldn't tell what the characters should be, I just removed it. Um, and then also just as a note, a lot of the numbers were removed and replaced with less than sign, pound, greater than sign. I went ahead and left this alone. Those numbers were probably taken out for privacy reasons, the phone numbers and things like that. And I went ahead and left them as is. It's possible that having the real numbers could make the processing, the accuracy a little bit better with these methods, but that's not something I can't determine, and something that could use testing in a real environment to see if that specificity is useful or not. Now, having done the text preprocessing and code, I brought it into RapidMiner. The paper talked about two ways to tokenize the data to turn it into numerical values that the machine learning algorithms could use. The first is the space character plus period, comma, and colon. And the second set of token characters are those 4 plus dash. And it's actually that second one that, at least among the top algorithms, proved to be the best. Besides the tokenization, I tried some further preprocessing steps. The paper that gave rise to this corpus suggested that that further preprocessing will hurt spam detection. They reference some email spam papers. And so I tried lowercasing all the data, filtering stop words, stemming, and creating n-grams. And in general, in almost every case, this resulted in lower accuracy. And in particular, when I created the n-grams, this added a whole bunch more data, whole bunch of extra features, and definitely slowed down performance. Now let me talk about the algorithms I ran. I ran 8 of them, and I want to split them into 2 categories. The first are ones that run quickly, and going back to that third goal of the algorithm needing to run quickly, these are ones that are not a concern for use in a production environment, at least based on my testing. They are decision stump, deep learning, k-nearest neighbor, naive Bayes, perceptron, and SVM. Then I ran 2 algorithms that did not run quickly, LDA and neural network. They did not run quickly, and so to try to improve performance and also to improve accuracy, as it turns out, I needed to do some dimensionality reduction. So I used PCA weights that were come up with by information gain, weights by information gain ratio, and weights obtained by running SVM. And as we'll see as we go along, the weight-based ones actually did improve performance, didn't really do anything for accuracy. If anything, they tended to reduce the accuracy. PCA improved the accuracy quite a bit of both LDA and neural network, but it has its own performance penalty that I'll get to momentarily. So in talking about the results, I'm going to mention a few of these in passing and then talk about 3 in more detail. These 5 here, decision sum, k-nearest neighbor, LDA, naive Bayes, and perceptron were what I call underperforming. You look at the measurements I used. Spam caught is pretty obvious. Ham blocked is something I wanted to minimize. Block very few legitimate messages, and that's something that I'm going to emphasize in these results. And then the overall accuracy. You see the decision stump was poor based on its how much spam it caught, or how little spam it caught. And then naive Bayes was decent. And then as you move to k-nearest neighbor, LDA, and perceptron, things get better to the point where you're almost into the top 3, but fall just short. Now I'm going to talk to the three algorithms that perform the best. The first I'm going to talk about is deep learning. Deep learning in my case, is very dependent on the activation function you use. So I tried, I believe, all the ones that RapidMiner exposed, and also did some testing with dropouts. The default rectifier was decent, but the TANH, I'm not sure how to pronounce it, but TANH is what I'm going to call it, had the highest overall accuracy. If I introduced some dropouts, 10% dropouts to TANH, it actually had a higher rate of passing legitimate messages. But because SVM is actually better at that, I decided to choose TANH with no dropouts because that provided the best overall accuracy and in particular the best percentage of spam caught. Next, I want to talk about neural network, which is probably the most interesting case. As I mentioned before, this is one of the algorithms that took a long time to run, so long that it would be difficult to use, or probably impossible to use in a production environment with something that as time sensitive as text messages. Um, and as you can see, with no dimensionality reduction taken, its performance is rather middling. And if I tried using weights from information gain or from SVM, it's actually drops a little bit overall. Information gain ratio actually was terrible. I didn't include it because it thought everything was a true message and really failed completely. It was only when I applied PCA that neural network came into its own, and you can see that the numbers jumped quite a bit. They fell just short of deep learning in overall accuracy and in its ability to not block legitimate messages. And you see some of the variations I tried. And I ended up rejecting it partly because it wasn't quite as good as deep learning, but also because while PCA made the neural network model run extremely fast, PCA had its own performance penalty, and when I timed it once, it took more than 250 milliseconds per message to apply its model, which is much too long when you think about text messaging, especially if you're trying to do this kind of processing on a user's device. SVM is the final algorithm I want to talk about and is actually one of the ones that I chose for the final solution. It, like deep learning, is very dependent on its activation function. The default of dot performs the best of all of them. ANOVA, and again, I'm not quite sure how to pronounce that, did slightly better at blocking spam, but not as good as at passing through legitimate messages. In fact, SVM has the distinction of being the only algorithm that did essentially perfect, or as perfect as far as 3 decimal places could tell me, at allowing legitimate messages through, which makes it very useful. Now, I wouldn't expect this to play out in real life. You can expect that people creating spam text messages would try to get clever and try to work around these, create messages that are closer to real ones. But it's a very promising result. And you can see the other tweaks that I made were based on the tolerance. And I found that a little bit of tolerance for misclassification in the dot activation function allowed for slightly better spam blocking performance while not hurting the number of legitimate messages that were passed. Before I show my recommendations, I want to circle back to the 3 goals. The first goal is the obvious one, to block spam SMS messages. And at this, deep learning did the best, catching just over 90% of the spam messages in my in the corpus I had. Second goal is to block few or ideally no valid messages. At this, SVM was a champ. I can't expect its performance to translate, that ideal performance to translate into real life, but it's very promising. Deep learning came in pretty close second, blocking of less than 1 in 800 messages. And then the third goal is to apply a model quickly, because we're dealing with text messages that we don't want to delay any more than we have to. Deep learning and SVM were both fine at this. They took minutes at most to both run and apply their models. Neural network had poor performance and had good performance only when PCA was applied. And PCA, as I discovered, took over 250 milliseconds per message to apply its model, which is not acceptable in this case, and thus it needed to be rejected. So let me finish out with some recommendations. There are 2 algorithms that stood out, and really for different reasons. The first one is SVM. It stood out because it blocked, best I could tell, no legitimate messages. And while you can't expect this to happen in real life, it's a very promising result. And it would seem to be the best algorithm to use in cases where you know the sender. So if you're running on a mobile device, if you're applying this model on a mobile device, it would be the person that's in the context list, for example. If you're running this on a server, you may use this algorithm when the recipient has already sent a message to this person, and so they've established a relationship between themselves. And so in this case, blocking no or essentially no messages is paramount. Now, when you aren't sure of the source or you're suspicious of the source, then SVM may not be the best choice. Here, I think deep learning is the best because it blocks very few legitimate messages. And you can see it's like 1 in 800 that it actually blocks as far as legitimate messages go. And it has the best span protection of any of the algorithms I tried at just over 90%. And so if you're unsure of a source, you can use this to get the best span protection while still being quite good at allowing legitimate messages through. And with that, we reached the end of my presentation. Thank you very much for watching. It's been a very interesting journey for me. This is my first real exposure to machine learning in practice and using RapidMiner on my own. And it's been a very interesting, rather exciting journey, to be honest. And I think came up with some good results. Thank you very much. Bye-bye.